Okay, let's start. Okay, so we are currently studying the interval estimates of the differences of the two means from the two populations. Okay, so we not our current setting is that we have two samples, which means one sample is composed of these and the other sample is composed of these, and then this one comes from a particular distribution, and then the other one comes from the other distribution, and then we are interested in answering the question of whether the two means from these two populations are the same or are they different. Okay, so that way, we compute this statistic, which is a sample mean from one sample from, and then subtracted by the sample mean from the other sample, and then if it's close to 0, and then we can conclude that these two populations have the same mean, but if they have a quite different value, and then we can conclude the other way, and then we modeled this guy as a normal distribution because each of these sample means are Gaussian distribution. And then they are also considered as a normal distribution. I mean, in particular, each of these two distributions are all assumed to be the normal, and then these are the subtraction between the two normal distributions, and thus they are also normal, and then we can compute this variances as well, and that way we compute this kind. So this guy, each of which will follow the Gaussian distribution of v1, and this guy as a variance, and for this guy will have the mean of this guy and then the variance of this guy, and then after standardizing them, and then we can see these this statistic is following the standard normal distribution, and that way we did a interval estimate of this guy, right? So we are typically manipulating this inequality in terms of this value in the middle, right? And then our statistic and some other values will determine the minimum and the maximum value for our interval estimate, and then that will associate with some alpha value, right? So if we want to have this confidence level, and then alpha is 0.5%. Okay, and then similarly we can do this one-sided interval estimates as well. And then now we were discussing the case where the variance is an unknown. So the overall story is quite similar to the previous case, where when the variance is known, and then we model our statistic. Where is it? Our statistic as this standard Gaussian distribution. But if our variance is unknown, and then we have to replace it with the sample variance, and then the distribution just changes into the t distribution. Okay, so here when this variance is an unknown, let's review the situation again. So we have two different distribution. Okay, they have two different means, and then we are still interested in the interval estimate of this difference of these true means. Okay, and then as I mentioned, the variance is unknown, but still our assumption is the variance from these two different distributions are the same. although we do not know what that value is, but we still assume that those two variances are the same. Okay, but we do not know what this value is. Okay, and then from one sample, suppose x1 was maybe 3654, x2 was maybe 43275. In this case, we call it as y and x, and then in this case, the sample size of an x is 4, and the sample size of a y, which we denote as m, is 5, because we have 5 samples and 4 samples each. Okay, and then we can compute the sample variance from each sample of an x and y separately, and then we divide it by the true variance and then multiply it with the n minus the sample size minus 1, and then it will follow the chi-square distribution, and that's what we learned previously, right? But the degree of freedom was, in this case, n minus 1, which is in this case 3, which is 4 minus 1, and 5 minus 1, which is 4. Okay? And then how about this? What if we just add them together? So when studying the chi-square distribution, if these two chi-square distributions are independent with each other, and then when summing them up, and then they will still be a chi-square distribution, but the degree of freedom will be the sum of the 2 degrees of freedoms, right? Because chi-square distribution is, by definition, it is a summation of squared standard normal random variable, right? So it's like xi squared, no, it's like zi squared, right? I starting from 1 to 3, right? And then in this case, we have another zi's. Let's say we call it as j, and then j starting from 1 to 4, right? And then when adding them up together, then they will still be a chi-square distribution, because we can still represent them as a sum of independent standard normal random variable. But the degree of freedom will be just added up together, right? So this one had this degree of freedom, and this one had this degree of freedom. When adding them up, you will have this degree of freedom, which is the summation of these two. Okay? Okay, so in this case, it was the case corresponding to, it was the case where we know the true variance, okay? And then the point is, our trick that we are gonna apply in this case is to change or replace this guy with some sample variance, and then this overall statistic will change into this, the t distribution or t random variable. So that is the story, and let's see how we can do that in detail. We actually define some new sample variance. So previously, in this slide, S1 squared and S2 squared are the sample variances from, computed separately from each sample of an X and Y, right? And then we can now think of some kind of a averaged sample variance by incorporating these two all together, okay? So that is called this, let's see, where is it? This is called a pooled sample variance, okay? Pooled means something like adding those two together, okay? So P is an initial of this pooled, and then let's look at this. Okay, and then we just incorporate these separate sample variance and then multiply them with its degree of freedom. So if we recall the definition of S1 squared and S2 squared, each of them had these denominator. So we are just multiplying these denominator so that we can change them in the form of summation of squared normal distribution, squared random, squared standard normal distribution. Okay, but it needed to have like m minus 1 s1 squared, and then we needed to have this guy, and that way we can change them as a sum of standard normal random variable, right? Okay, and then let's just ignore this part. Okay, let's just focus on the numerator, and then we multiply them with its own denominator it originally had, and then it became close to the summation of some kind of standard squared standard normal random variable, right? But yeah, let's ignore that, and then let's consider this guy divided by sigma squared. Again, two samples of an x and y, they have the common variance. I mean the true variance parameter, although we do not know what that is, right? And so if we divide this by sigma squared, and then finally this one will become what? Which distribution? Which distribution? It will be what? It's the chi-square distribution, right? And then what will be the degree of freedom? This guy had a degree of freedom of n minus 1, and this guy had an m minus 1, and then the degree of freedom will be n plus m minus 2, right? Okay. Okay, and then let's recall the definition of the t distribution. So t distribution needed the Gaussian standard Gaussian random variable in the numerator, and then what about the denominator? It had x degree of freedom of n divided by n, right? Okay, so if we can have this z in the numerator, and then if we can represent this guy by using our pooled sample variance, and then we can construct this t random variable, right? Okay, and then now let's consider this denominator at this point, and then by definition our pooled sample variance contained this denominator, right? And then even though it doesn't have this guy, right, but fortunately we have this here, right? And so if we can define this pooled covariance, sample variance in this manner, and then divide it further by sigma squared, and then we now have this guy in the denominator, and then this guy by from the definition of this pooled variance, right? And then this guy will correspond to this part, right? Chi-square distribution divided by its degree of freedom. What was the degree of freedom? This guy, n plus m minus c, right? Which we included in the original definition of this pooled sample variance. Okay, then now this guy, we can understand this guy corresponds to this part, which is a denominator of this t random variable, and then let's consider this z. And then what about z? Z can be constructed in this manner: this guy and minus this guy, and then although we do not know sigma squared, but we can understand. We already studied this guy follows a standard Gaussian random variable. The only difference from the previous case is that sigma squared is not known, it's unknown, right? So that's the only difference. Okay, and then this guy is z, and then this guy is corresponding to this, and then now this sigma squared, and here we have a sigma squared as well, and they will cancel out, right? They will cancel out, and thus altogether, yeah, if we just manipulate this expression, and then we will obtain this expression, which follows the t distribution, okay? And then the degree of freedom was what? So this was the degree of freedom for the t distribution, and in our case, the degree of freedom is this n plus m minus 2, right? So altogether, we now have a conclusion that if we compute this statistic, okay, which is requiring x bar and y bar, which are the two sample means, and also we have to compute this statistic, which is our pooled sample variance. And how do we compute that? It is defined by this, right? So it didn't have sigma squared, and then it's just a weighted kind of weighted sum of these two separate sample variances. Okay, so we have no problem in computing this SP squared, and thus we just plug that into this expression, and that way, yeah, we can just construct this value following the t distribution. Okay, then the rest of the story will pretty much the same. Will be pretty much the same. So this guy, yeah, in the case of two-sided interval estimate, and then given some confidence interval, when alpha is 0.5%, and then it can be 95%, and then from the t distribution, yeah, it's like yeah, this area, it will be alpha over 2. It's exactly the same story, right? So we extract out, we obtain these values from our table, right? But we have to use the t distribution table when the degree of freedom is this particular value. So we need the number of samples from x and y. Yep. And then if we manipulate this so that mu1 minus mu2, yeah, having the lower bound and upper bound, and then that's the final answer for our interval estimate. And then similarly, one-sided confidence interval or interval estimates can be also obtained as well. Any questions so far? So these confidence intervals will appear once again in the next chapter in a different context or with the different goals in mind. So in the next chapter, it's about hypothesis testing. Okay, hypothesis testing. So in this case, we are interested in obtaining the interval estimates representing this difference of these two true means. Okay, but in the next chapter, our question that we want to answer is, yeah, has the form of are the two true means from these two populations different or not? So are they the same or different? So we want to answer this question in terms of a yes or no answers. Okay, but they use almost the same kind of technique. Okay, so yeah, please familiarize yourself, yeah, in this kind of a yeah, manipulation or the formulation as well. Okay, and yeah, so yeah, we can view or understand this pooled sample variance as also a particular type of an estimator for our sigma squared. Okay, and yeah, so such an estimator is defined by this. Okay, now we view this statistic as an estimator that we want to use to estimate this true parameter value. Okay. So in this case, if you follow, if you apply some similar techniques used to prove this guy is a unbiased estimator, or things like that. So kind of unbiased estimator, the definition of it. So we just consider this expectation value, and then the expectation of it will be the same as sigma squared. Okay. And then intuitively, we can think of it as this kind of process. So let's use this kind of sample. So only using the first sample, we can also estimate, or we can also obtain the estimate for the true sigma squared, right? How? We compute the sample mean, and sample mean will be 4.5, I guess, right? And then we subtract like this value from 3, 6, 5, and 4. And then we just take the square of them and then sum them up, and then divide it by what? Divide it by 3. Because that 4.5 is a kind of a fluctuating or kind of a approximate one. That is not the true mean, right? So that's why we kind of have to divide it by n minus 1, right? And then we can also utilize the sample y in order to estimate the sigma squared, right? So it has its own mean value, and then we can compute the sample mean, sample variance from the sample y, right? And then if the two distributions have the same variance value, okay, the same variance value, how can we utilize these samples in order to have a kind of better estimate that fully utilizes all the available data that we have. Okay, so that's the main idea for this pooled sample variance. So here and then what if we can just merge them together into one single sample? Okay, and then compute the mean value of it, and then subtract that common mean or single mean value from each of these observations from these two samples. Can we do that? I mean, yeah. Would it be a kind of correct or reasonable way to do so? So in this case, we cannot do that because our assumption here is that, okay, so the first sample and the second sample follows the Gaussian distribution, but those two Gaussian distributions are different ones. And in what aspect are they different? They can have a potentially different mean value. So mu1 and mu2 are different, okay? But their variance are assumed to be the same. So that was the assumption, okay? So we have to apply the sample mean computed separately from the first sample and the second sample. Okay, so let me just maybe change it into more and kind of a clearer kind of example. So instead of this sample, because the mean of this guy looks just similar to the mean of the first one, right? So let's say, maybe let me just put 10. Let me just add 10 on each of these samples, right? And in this case, clearly the sample mean from these two samples look quite different, right? So that is kind of the situation that we are kind of dealing with in the current example. But the variance, looks like pretty much the same between the two, right? So in order to estimate those variance, we can fully utilize those two samples. by applying its own sample mean value. Okay. So that way, yeah, that way we obtain this and divide it by n plus m minus 2. Any questions? Okay, so yeah, these are just a summary. And yeah, so these are kind of summary table covering all the different cases that we studied. So in this example, again, we are interested in estimating the differences between the two true means from the two distribution, right? So that's why we have this x and y as a two samples, right? And then, yeah, we are interested in obtaining the interval estimate for this mu1 minus mu2. And then the situation was like when these two are known and they are unknown, but they are assumed to be equal, right? So we didn't study that they are unknown and they are not equal. So this is a too complicated situation that we do not study in this class. Okay. Honestly, I don't even know how to handle this situation. And then the next one, yeah, was just a one-sided version of them. Okay. So the only difference is this guy changes to this guy, right? So we put 5% probability. Yeah, split them into half and then yeah, distribute it in the both sides. In the case of one-sided test, one-sided interval estimate, we put all this probability into either lower or upper bound. Okay. And then now we are studying binomial distribution. Okay, so yeah, or this Bernoulli random variable, and then yeah, we obtain IID observations from the Bernoulli random variable. Okay, so that forms our sample. Okay, and then that, yeah, viewing that as a single trier, that was called a binomial distribution. Anyways, yeah, Bernoulli distribution is just having like two possible random variable values, 0 or 1, and then its associated probability, right? P and 1 minus P, right? And then let's call, yeah, let's suppose our sample was obtained as like 0, 1, 1, 0, 1, 0, 0, for example. Okay, so this is one example. Yeah, one example of our sample that we obtained from this Bernoulli random variables, right? Okay, then now the measure or the parameter that we want to estimate is the parameter p, because in the Bernoulli random variable we have possible value of 0 or 1, and then we have p and 1 minus p probability, right? And so this is the only parameter, so we want to estimate that. And then from viewing that as a binomial random variable, we know that the sum of x, so the number of ones that we obtained out of n different trials, okay? So let's call that as this x, okay? So even though it didn't show the definition, but it's a computed, it's a particular statistic obtained from our sample, okay? And then that is the number of ones, okay? So in this case, it will be 3. Okay, and then this value is exactly a binomial random variable, and then we know that it has the mean as np, and then variance as np times 1 minus p, right? And then if n gets larger and larger, then we know this guy follows approximate. So this dot is representing some approximation. It's following this Gaussian, standard Gaussian random variable. Okay, then now, we can use this statistic in order to estimate this true parameter p. Okay, then given this alpha value, we obtain this. And then what was the next step? We have to manipulate, or we have to clean this inequality so that we can obtain this form. P lies in this between this lower bound and upper bound. So that is the final form that we want to obtain. And then if we can obtain these two values as a particular value, and then that will be our interval estimate, right? But here it is not very easy, or it is not straightforward. So let's look at the reason. Okay, and then we can just multiply this guy into both sides, and then we obtain this. And then we add x to each side, and then divide each side by n. Okay, divided each side by n, and then we obtain this p, right? And then x moved to each side, right? And then x was divided by n because we divided by n, right? And then plus we have this, and then we are dividing it by n, and then it will become squared, getting inside of this square root, and then we finally obtain this value. Okay, and in this case, even though we obtained the inequality that specifies the range or the lower and the upper bounds of this p, but this part had x over n. So what was an x? So in the previous case, x was 3, and what was n? N was 1, 2, 3, 4, 5, 6, 7, n was 7. So x divided by x over n will be 3 over 7. Okay, so far so good. So that is this part. But in this part, we still need these p. Okay, so p value. So p is the parameter itself that we want to estimate, right? So our unknown variable is included or contained in this lower and upper bound, right? So that doesn't make sense, right? And so one quite simple trick that we use is to use this approximate value of p hat, which is x over n. Okay, so that is just an approximate kind of a point estimate of our p, right? Then I think we studied that this x divided by n is maximum likelihood estimate for this point estimate of this true parameter p in the binomial random variable, right? So please review them. So I understand that. Yeah, so in our exam, in our previous exam, I just yeah we just had the problem of this maximum likelihood estimation for the true mean and the variance value in the Gaussian distribution, right? And there was the example, just an example in our textbook, right? But surprisingly, not many students scored this problem. So I likely, so we are studying the probability. So there is a high probability that I will prepare for the I will have the same or similar questions like that in our final exam as well. Okay, so please review them again if you're not have a confidence about that part. And then but anyways, okay. And then, so we are replacing this unknown parameter value as a with some approximate point estimate that we have as this x over n. So that is a little bit kind of a simple trick that we incorporate. So this one has a little bit of an inaccurate kind of aspects or inaccuracy into this interval estimate, but that's what we usually do. But still, at a high level, so we followed the fact that this guy is following the standard Gaussian random variable, okay? And then this guy had kind of a mean value, and then this part was the variance value times this z threshold value. Okay, let's look at some example. This example is a little bit. So I think so the new homework came out right last night or so, and then as you will see, you have to properly understand all the lengthy kind of sentences, right? So that is also kind of challenges in this course. So there are many different situations that each of these exercise problems are describing. Sometimes it's talking about some manufacturing kind of factories, and sometimes it talks about some politics and some kind of polls and so on. And then it can be kind of lengthy, right? But you have to kind of closely follow what this means. So that's the part. That's the part that you have to train yourself on in this course. Okay, so recent poll indicated 52% of the population was in favor of this job performance of President Obama. So 52% of the people was shown to like Obama's kind of policy and so on. And then it says the margin of an error is plus minus 4%. Okay, so it's like overall it obtained P as a point estimate with this value, and then something like 52 plus 4% and 52 minus 4%. Okay, and then what about this guy? What about this guy? This guy will correspond to this representation, right? So we can just plug them in. So in this example, it didn't even show what the confidence interval is, but in the solution, it is a common practice that if the confidence interval is not shown, and then the common value is 95%. Okay, so it's a two-sided test two-sided confidence interval. Then we put the 2.5 probability, and then we know this z value is 1.96, right? 1.96, right? And then let's just plug these values as well. So what about p hat? So p hat is 52%, right? So 52%, and then this guy is 1 minus p, which is a point of 48%. Okay, and then altogether this guy should be 4% or 0.04. So the problem here is that we need to obtain or compute proper n value. So number of samples. I mean the sample size, number of observations. Okay, and then if we just solve this equation in terms of an n, and then n will be this number. So this New York Times would probably conducted this poll on this many number of people, okay? And that's why they have obtained this plus minus 4 point of an error, or this kind of confidence, the interval estimate, which is corresponding to this part or this part. Okay, so in this case, it is just the same representation or same mathematical expression. So if someone says or someone gives this confidence interval length or width as b, which was like plus minus 4%, and in this case, the length of this interval will be 8% because it's like a positive and negative 4%. And so this b value or 8% will be the same as this value. So plus minus this value, right? So we have 2 here. Yep, and then we can just compute the value of an n by using this expression. And then if we manipulate this guy, and then we can obtain this expression. And that represents the number of observations in our sample. Okay. So in general, if we want to have a narrower or smaller interval length, okay, smaller interval length, and then the n should be bigger, right? So that is an obvious part. And then let's look at the next example by using this formula. Okay, so we want to have this 99% of the confidence interval. And then the length, I mean the p, we have a p, and then the interval length or confidence interval length is set as 0.05. Okay, and then here, it had another setting or additional setting that initial sample of 30 chips has been taken, and then among 30 samples, 26 of them were having the acceptable quality. Okay, and then so here the question is, we have to obtain this required number of observations in order to ensure this much of a confidence interval length. Okay, so n is an unknown, but in order to apply this expression or this formula, this b is confidence interval length, which is a 0.5, okay, 0.05. So this is a 0.05, but also so this guy comes from this confidence interval, 99%, right? And then what about this p hat or p star? in this case. So initially, or the previously, when obtaining, remember this expression. When obtaining the confidence interval length for P, we needed the true parameter value P, but we just used the approximate value of P, right? But in that case, when obtaining or computing this value, we needed to have this guy, the number of ones divided by the total number of trials, right? But here, we do not yet know what the number of observations are. So n is even unknown in this case, right? So n is even unknown. So suppose n was, the required number of observations were maybe, in this example, like, about 600 people. And then, before having this number, we cannot even obtain this approximate p-value, right? So in this example, another trick that we used in this example was, so n is a much bigger number. So for example, if we just pick the answer, and then this is the required number of samples, okay? So about 1200 observations are needed in order to ensure this confidence interval width. But in order to obtain this approximate p-value, we just perform some samples with the small number, of observations. So out of 30, we obtained 26. And then by using these small numbers of observations, we can obtain this approximate value of p. Okay, so this value is plugged into this p star. And then now we can obtain, we can compute the required number of samples, n, or required number of observations, right? And so that is this formula. So n and 2 times this squared, right? Because n was originally inside of this square root. So that's why this 2 gets squared. And so that's why we have 4. And then this guy squared. And then this guy comes from, this B part, right? Which is a required confidence interval length. And then what about this guy? This guy is this approximate value. And this guy is 1 minus this approximate value of P. Okay, and then this is the required number of observations. And then we already obtained the 30 samples in order to, although it's an inaccurate one, but we obtained this value P. And then from this process, we already obtained the 30 samples. And then additional number of observations that we need when these 30 observations are already obtained. And then we can just compute the difference between these two. So additionally, we need around 1200, in this case, observations are needed in order to ensure this confidence interval length. Okay, and then after all, if we just recompute, if we recompute confidence interval for P, so when computing the required number of an observation n, we used this more kind of a less accurate one, right? But now we have a little bit more accurate kind of estimate for P, which is this guy. So so suppose we used this required number of observations, and then overall, out of them, these numbers were obtained as a positive 1, okay, positive 1, and then out of this number, this number plus 26, right? So that is the total number of positive samples that we obtained. So this one is more kind of accurate P because it used much more number of observations. Okay, and then we use this more accurate version of the P, although it's still a kind of approximate one, and then we obtain this interval estimate, okay, by using this number of samples or this number of samples, and then this is the final result. The final result as the interval estimate for P. So when computing the differences between the two, it's approximately 0.04, 0.05, maybe 1, and so on. Okay, so this guy, yeah, this value can be a little bit bigger or slightly smaller, right? Because in this place, we didn't use this kind of less accurate one, right? So we used a little bit more accurate one, but that value can be different from that value, right? So yeah, this interval can fluctuate a little bit in a way that the interval length can be a little bit bigger than 0.05 or smaller than 0.05, right? But yeah, so this is a kind of entire kind of procedure to solve this problem or this example. Any questions? Okay, and then this is probably probably the last thing that we learn within this chapter. But in this chapter, it gets a little bit dirtier than the previous example. I mean, we use even more approximate kind of approximation into this process. So yeah, so we are discussing the required number of observations, right? In order to ensure some pre-given interval length or interval estimate, right? And then in this formula, which is just this guy, okay, so we are still talking about this formula. And this although it looks a little bit kind of a new kind of formula, but this is just a simple manipulation of this formula. So at this point, you should be able to understand this formula because we are giving this interval length, but also this part, it's just coming from this part, which is coming from where? This part, right? Oops. Okay, so yep, so this is that formula that we obtained in the previous slides. And then what did we do when handling this P? So we kind of replaced this true P with some approximate estimate of P hat or P star. So in this case, it was used as this approximate value of P, right? And then this can be kind of inaccurate value of P, right? So instead of using this inaccurate value of P, let's just consider kind of worst case scenario. So as I mentioned in the previous example, so if our initial estimate of the P, okay, by only using the 30 sample, suppose that value was quite different from this value or the true P value, and then based on that, I mean the required number of observations, which is n, computed in this manner by using that inaccurate one. So that can be kind of an unreliable one, right? So even after we obtained the value of an n in this manner, after all, if we compute or obtain this interval estimate, and then that can be a lot larger than 0.05 of an interval estimate or interval length, right? So overall, in this example, our goal is to ensure this interval length to be 0.05, right? If it gets too big, and then it's not a good situation, right? So we want to ensure that 0.05 as our intended interval length, right? Okay, And then let's now think about, if we understand this P, P to be kind of an inaccurate one, and then how about just using, how about just thinking of some worst case scenarios. So regardless of what P value is, we want to have some kind of a required number of observations, that can guarantee that this kind of interval length to be less than or equal to 0.05. Okay, so that is the scenario about this slide. And to this end, or with this kind of goal in mind, what we do here in this example is we can just think of some maximum possible value of this representation. Okay, and then as I mentioned, these are the fixed value, and then P times 1 minus P can vary, right? So if we use a P as a kind of a more accurate version, and then that will be kind of a more reliable value. But if P is an inaccurate, and then that value is not kind of reliable, right? So what will be the maximum value, maximum possible value for this part? Okay, so P times 1 minus P may be small or large, right? And then what will be the maximum possible value? So that the required number of samples to be largest one. Okay. So so let's just look at this function, f of P. So it's a function of P, which is P times 1 minus P. Okay, and then it is P minus P squared, and then we do the manipulation that we did in our middle school or high school, minus P minus 1 over 2 squared plus a quarter, right? Okay, so let's draw the function of this in terms of P, and this is f of P. Okay, and then it will have having this form, right? So the reason I didn't draw like this part is because the range of P will be between 0 and 1, right? It cannot be a negative value, or it can be more than, it cannot be more than 1, right? So we can only consider such kind of range between 0 and 1, right? Okay, and then overall, this function value or this value, what is the maximum value? So the maximum value is this value, right? 1 over 4. 1 over 4. And thus we can just plug this value as the maximum value as 1 over 4. And then it will, it will give you the worst case, the number of required samples in the worst case, right? So if the true P was smaller or larger than this 1/2, and then the actual required number of samples will be actually smaller than this worst case. But we are just considering this worst case scenarios by just plugging this P as the maximum possible value. I mean the value such that this part or this part becomes the maximum possible value. Okay, so that corresponding value is 1 over 2 or 1/2. Okay, so if we plug this guy with the 1 over 4, and then we obtain this value, because we can cancel out this 2 squared. Okay, so that way we can kind of solve some problems that you have where you have to solve this number of required samples in this Bernoulli kind of cases. Yep. And then similarly we can do kind of one-sided lower or upper bound interval estimates. by using the same standard Gaussian random variable. I think that's it for this chapter of chapter 8. 7. Any questions? 네. 피해시랑 피해시 스타라. 네. 오, 날카로운 질문이고요. Okay, so that is a good question. The question is, what is the difference between p hat and p star? Yeah, so p hat is the value. So when considering this p hat, the problem is not about solving n. So n is already fixed, right? And then the main question that we want to answer here is, to obtain this interval estimate of the p. Okay. So in that sense, p hat is an approximate estimate of p, but our number of observations are already fixed, and then we have a full observations or full data that we obtain from this n number of trials. But when determining this n, or the number of samples, right, in this case, just like this guy, where we used only a small number of samples or small number of observations, right, by using some initial number of samples, right? So this is called a p star. So this is an even worse or even more inaccurate one than p hat. But it's just a notation difference. Okay? That is a good question. Any other questions? Okay, then next chapter is hypothesis testing. So I briefly mentioned about it. Maybe 20 minutes ago. So here we want to answer some question. Okay, and then this question involves two different hypotheses, two kind of conflicting hypotheses. So if one is true and then the other is automatically false, and then the other is not true, and then the other becomes true. So it's like the first, so when answering, so when considering like two different means from two different populations, our question is whether the two means are the same or the different. Okay, so we consider these two hypotheses or two scenarios, and the first scenario is those two true means are the same. And then the other hypothesis or the other scenario is that two true means are different. Okay, so in this case, this one corresponds to this guy, and this guy, this hypothesis or situation is corresponding to like this. Okay, but just like similar to like two-sided versus one-sided test. Two-sided or one-sided confidence intervals that we studied in the previous chapter. The first hypothesis can be in this form, but also the second hypothesis or second scenario can be something like mu1 is mu2, or mu1 is smaller than mu2. Okay, so that those situations will correspond to one-sided confidence interval. Okay, so we will study these different scenarios and how to answer these questions. Okay, and then these are you have to first study those different terms introduced in this chapter, like yeah, we can understand what these hypotheses mean. So these are kind of two different situations or two different scenarios that are conflicting with each other, right? But one of them is called a null hypothesis, and the other is called a alternative hypothesis. And then also we have these terms of type 1 error, type 2 error, and then critical value and critical region and the acceptance region and so on. And also the verb or the term that appears quite often is this guy. Where is it? Yep. Yes, the word reject. Okay. So it's like so these are a little bit requires a little bit of a learning curve when you study this chapter. So please make sure to memorize those terms and the meaning of these. So this is the first starting point when you when you study this chapter. Okay. Okay, and then let's look at these hypotheses in more detail. So we consider this null hypothesis and the alternative hypothesis, and the mathematical notation is H0, or it's called H naught. Okay, H naught. So I don't know why it is called naught, but oftentimes when having these zero as a superscript or a subscript, and then we just say it as naught. Okay, H naught. Anyways, so that is null hypothesis, and another one is alternative hypothesis, and then usually this null hypothesis corresponds to some common belief. Okay. And then the other one is a little bit more kind of interesting kind of scenario. So suppose you work in some pharmaceutical company or something. I mean, the company that creates some new medicine, and then you kind of invented a new medicine, and then you want to prove that this medicine has some significant effect or some non-trivial advantages. Okay, so in that case, suppose the previous Tylenol, suppose the existing medicine was this Tylenol, and then you maybe invented another medicine. And then you want to show that your medicine works much better than this existing one. Okay, but many people will not believe that until you provide a sufficient amount of an evidence, right? So this null hypothesis is corresponding to the situation that your new medicine has no different effect than the previous one. Okay, so that is corresponding to a little bit of a common belief, right? So this is a kind of default stance that we will take when given no available data supporting the other scenario. Okay, so this is a kind of default situation that we are taking. Okay, and then in the other cases we have a 2 factories, and then our kind of default belief is that their defect rates are not different, so they are the same. Okay, and then when sufficient amount of data or evidences are given in a way that these common beliefs are wrong, okay, so that's when we reject or we throw away or we abandon this default hypothesis or default common belief. Okay, so that way we say that we we reject the null hypothesis, and when this sufficient amount of data says we have to reject it. Okay, supporting the another scenario. Okay, and then alternative hypothesis is the other one. So when we reject this null hypothesis, and that's the same case, or that's when we accept this alternative hypothesis. It's a little bit kind of surprising surprising fact or scenarios. And then there can be two different types of an error. So your null hypothesis or default belief was actually true, but your data was saying your data looks like saying abandoning our existing belief. Okay, so we will reject our null hypothesis in this situation, but it was a wrong decision. Okay, so this is a type 1 error. So what is the true? What is the true hypothesis? The null hypothesis is true, but we wrongly rejected it, or we wrongly accepted the alternative hypothesis, right? And then, in that case, the probability of an error corresponding to this case is called a significance level, and we denote it as alpha. And then, what about type 2 error? So it is the opposite situation. So the null hypothesis is actually not true. So we should have taken the alternative hypothesis as as true, but we didn't reject it. Okay, we didn't reject the null hypothesis, but it was wrong decision. And the probability of this committing this kind of error is denoted as a beta. Okay. So we can think of these 4 different situations, and this is called sometimes it's called a confusion matrix. So H0 was true. So this situation is the primary situation when type 1 error is considered, right? So in type 1 error, when saying this error, the true situation was, the situation was the null hypothesis is true, but we rejected it, and it was wrong decision, right? Okay, so let's think of this situation. It's like thinking of some kind of conditional probability. So here, the condition or the initial situation is that the null hypothesis is true. Okay, so in that case, we rejected it and it was wrong, and that is corresponding to this type 1 error, and the probability is alpha. And then the other one is a kind of correct decision, and it corresponds to the case that we didn't reject H0, so there was not sufficient kind of evidences that makes us reject our hypothesis, null hypothesis, and the probability will be 1 minus alpha. Okay, and then in terms of beta is corresponding to the situation where the null hypothesis is not true, right? So in this case, we didn't reject it and it was wrong. And that case is probability is beta, and then the other probability is 1 minus beta. Okay, and then so in general, we want to minimize these both of these two types of an error, but in reality, we cannot minimize fully both of these two errors. So these are kind of a trade-off relationships. So if we are focusing on minimizing the first one, so we have to make this guy to be a little bit larger. Okay? So they are kind of a trade-off relationship. So we will see this by using some detailed examples next time. Okay, and then time's up. So let me continue from this slide. This Thursday. Okay, thank you. 그래, 또 안 갖고 왔네. 그거 다음 시간에 갖다 줄게요. 네.